yesterday what we talked about was that if you're taking the integral of some function, like y equals x squared, wow, that's terrible.
That's awful. That was pretty bad.
It just wasn't the same.
It kind of, it isn't really even on both sides.
Anyway, if you're trying to take the integral for people who are absent, in this case it would be from 0 to 3. And what I would be trying to find is the area underneath this curve from 0 to 3. Okay, that's basically what the integral is asking me for. It's asking for the area under a curve from something to something else. The good thing about yesterday was we knew how to find all those areas with formulas. We had rectangles, we had triangles,
That's cool.
trapezoids, circles, but we never had anything that we didn't have an area formula for until now. I think there is actually an area formula for this. Someone figured it out, I forget who. But one of those like old guys actually came up with a formula for the area under a parabola. But we don't have that. So this guy, Riemann, it's called a Riemann sum. Riemann. Right, okay.
Can I guess what it is?
No. This is probably what you guys started talking about in physics, that if we take this area and we divide it into rectangles, we can take the area of those rectangles and we can use it to approximate the area under the curve. So for people who, how many people have never heard of this before? Okay, good. So for people who have never heard of that before, we're going to go through it so you see the mechanics. It's really an annoying mechanics to do, but whatever. First, let's say we're going to split this into 3 parts because that makes it easy. And I'm going to make rectangles out of these parts. I'm going to split it into 1, 2, 3 pieces. And I don't know what the area formula would be between like this, like 3/4 of a rectangle and a curve, so I'm going to make a rectangle out of this. I'm going to make a rectangle here, make a rectangle here, make a rectangle here. And I'm going to find just the area under the rectangles. So the area under the rectangles is going to be like this, all of this, and all of this. It's obviously just an estimate. In this case, the area that I find is going to be an overestimate. It's going to be too much because I have all this space that's being included in my area, in my answer, that's not actually under the curve. So to find this area, I literally find the area of rectangle 1, the area of rectangle 2, and the area of rectangle 3, and I put them all together.
This is really annoying.
Yeah. So,
why are we doing this?
because, shut up. This curve is y equals x squared. That's what's going to allow us to find the height of each rectangle. The first rectangle has a width of 1 and a height of what? 1. My second rectangle also has a width of 1 and the height this time of what? 4. Okay? I'm using 2 as my like endpoint. I'm going up to where it hits the curve and I'm using that height of 4 because I'm plugging it into x squared. And my other rectangle has a width of 1 and has a height of 9, 3 squared. So I've got a rectangle, or an area of 1, an area of 4, and an area of 9. I put it all together, and I have 14. So 14 is one estimate for the area underneath the curve y equals x squared. And it's not a great estimate, because I only used 3 parts. So I could say an overestimate is going to be 14. So I know that my answer is going to be no bigger than 14. The actual integral is no bigger than 14. What I just took is called a right-hand sum. And it's called a right-hand sum because for every rectangle that I had, I picked, like if this is the width of it, I went to the right of that width and used that height as the height of the rectangle. For this one, this is my width. I went to the right-hand side and I went up to the curve and I used that as the height. And here I went to the right-hand side, went up to the curve, and used that as the height. So this overestimate was my right-hand sum, is what it's called. Sum. this whole thing in general is called a Riemann sum. So it's a way to estimate the area under a curve. Well, let's do the same thing, but let's use a left-hand sum. So if I use the same picture, but I use the left-hand sum, my rectangles are going to be different in height. They're all going to still be the same width, as long as I use 3 of them. But now, if this is my first, well, let me start over here. If this is the width of my first rectangle, I'm going to go to the left-hand side of it and go up so that this will be my first rectangle. My second one still have the same width, but I'm going to go to the left-hand side, go up to where it hits the curve, and that's going to be the height of my second estimated rectangle. The third one, I'm going to go to the left-hand side. Well, this one hits 0. This one's going to have no height at all. So its height's actually going to be 0. It just so happens if I go all the way to the left and I go to where the curve is, it's at 0, so this rectangle has no height. So these areas, let's call it like 4, 5, and 6. This was a right-hand sum. This one's going to be a left-hand sum. The first rectangle is a 1 by 0. The second one's a 1 by 1. And the third one's a 1 by 4. Do you see where I'm pulling all these numbers from? Yeah.
If it's on the negative side of the x-axis, right, would be an underestimate for the right-hand sum, an overestimate for the left-hand.
It depends on, it's going to totally depend on what the curve is doing.
Does it matter what we
If
call
it's
an
increasing
overestimate?
for the same function.
For this particular function, if I'm on the left side, then yeah. So in this case, I've got 0, I've got 1, I've got 4, so when I add it all up, I've got 5. So in this case, my underestimate is 5, and I got that from taking a left-hand sum. All that tells me is that the actual integral of x squared from 0 to 3 is somewhere between 14 and 5. What did he freaking do? I'm really sorry you won't get the 40 minutes of your life back, but I gotta keep going because it's actually on the text.
There's more of this?
Yeah.
This is crap.
Okay. Now, we have 2 more sums to do, but before we do that, we gotta talk about this overestimate, underestimate thing. It is not the case that an overestimate always goes with a right-hand sum and that an underestimate always goes with the left-hand sum. That just happens to be the way this one goes. Instead, I'm trying to think. You basically are always just going to be able to tell. So for example, let me give you like, I don't know, something that goes like this. If I go from 0 to A, and I split this into however many rectangles I want, and I say, is a left-hand sum an over or an underestimate? So not even like taking one, but is a left-hand sum an overestimate or is it going to be an underestimate?
Over.
So a left-hand sum means that for each rectangle I'm taking the leftmost endpoint and making a rectangle out of it. Leftmost endpoint's the height of that rectangle, leftmost is the height, leftmost is the height. So it's an overestimate. So in this case, a left-hand sum is an overestimate. You can always basically tell from the picture if you have an overestimate or an underestimate, and the question will be just that easy. Here's your function, is a left or right-hand sum an overestimate or an underestimate?
Do these Riemann sums have any actual application?
They lead us into what an indefinite integral is, but we're just not there yet. This is how it started. It's like this is kind of how integrals actually started and where the idea came from. The idea is going to be, I'll just give you a little, what's called spoiler alert, that actual integration, what it does is it uses rectangles, but it uses rectangles that are infinitely small in width, so that I actually am getting an exact, accurate amount for the area under a curve. So right now I'm using these rectangles that have some width so that I can actually add them up. I don't want to have like a million of them, but what actual integration does is it uses smaller rectangles so that I get a more precise estimate for what's under there. And they use an infinite number of them, so you get an actual amount of area underneath the curve. Yeah.
So for the test on the integration, like every answer is going to be a decimal.
No, not necessarily. No. Okay, don't hate me. Luke, don't hate the messenger, just hate the message.
So
In addition to left-hand sums and right-hand sums, there's midpoint sums. And there's also trapezoidal sums.
I hate. So back to these sums.
What?
If you want to find the underestimate, you can really just cut off the biggest one. Because that's essentially what you did there.
If I want to find an
If
underestimate,
you want to find the underestimate, you cut off the biggest rectangle in the overestimate. Am I right in saying that?
I want to find the underestimate. No, you want the smallest.
Look, when you took the underestimate, you didn't take the biggest rectangle.
Yeah, okay.
So you just cut off the biggest one.
No, but don't do that. It's just not the way you're going to be asked it. You're going to be asked to find the sum, the right-hand sum or the left-hand sum, and then determine whether that answer is an over or underestimate. Just real quickly, let's do a midpoint sum.
I like my one.
Yeah. It's pretty much that.
I'm sorry, I didn't make it up,
The
okay?
widths are different.
Let's use the same curve and go from 0 to 3. And use what's called a midpoint sum.
You just cut off one of the ends.
How do you think we're going to find the height of each rectangle with the midpoint sum?
In the
Oh
middle.
my gosh, you're right. So it actually makes more sense to use a midpoint, in my opinion. It's usually more accurate because you're not necessarily having an overestimate or an underestimate that's clear, kind of cutting some off and then having some extra. So for the height of each rectangle for this one, I'm going to go halfway, and that height is going to be the height of my rectangle. I'm going to go halfway, and that's going to be the height of my rectangle. And halfway, that'll be the height of the rectangle. So you can kind of see that now if I find the area of these three rectangles, I'm missing this part, but I have a bunch of extra here. So it's not going to exactly replace itself, so you're not going to get an exact answer, but it's going to be pretty close. Same thing here, like I'm missing this area, but I'm getting a little of that extra. I'm missing this, but I'm getting a little extra here. So if I go find this midpoint sum, the first rectangle is a 1 by what? What's the height here? 1/4. Okay, because in between is 1/2, squared is 1/4, because it's y equals x squared. The second rectangle is going to be 3/2 squared, so it'll be 9/4. And the third rectangle will be 5/2 squared, so 25/4. Put it all together. 35/4, which is 8 3/4. So the midpoint sum equals 8 3/4.
Pretty
So,
close.
so far we know that the left-hand sum or whatever it was gave us 5. The right-hand sum gave us 14. We know the area is somewhere between there. The midpoint sum saying it's 8 3/4. Let's find the trapezoidal sum.
Yeah, let's find the real one. Then.
We will.
Isn't it just 9?
Shut up.
Spoiler alert, it's 9.
Trapezoid looks like this. Okay, trapezoid one. I missed it. Probably was not made up by Riemann because it actually makes more sense than splitting it into rectangles. They split it all into trapezoids. And why that's helpful is you can just use this height, and I connect them, and I make a trapezoid underneath. And then I use this height, and I connect them, and make a trapezoid. And this height, I connect. In this case, it makes a triangle in the very end because this happens to come to a point, but it still would work under like the trapezoidal rule. So I'm going to have trapezoid 1, trapezoid 2, and trapezoid 3. Each one is 1/2 times the height times bases added up. What's the height of each trapezoid? First of all, do you see they're all on their side? That's why I was pointing out that one homework problem. All these trapezoids are on their sides because the parallel sides are the bases. This is the height. Okay, so the height is is actually not the way you think of it. The height's going horizontally. So the height of each trapezoid is 1. I'll start with my third one. I'll start all the way to the right. The bases are 9 and 4. The bases of the middle one are 4 and 1. And the bases of this one are 1 and 0. You could have just treated it like a triangle, but whatever. So I end up with 1 half, and 5 halves, and 13 halves. Put it all together, 19 halves, which is 9 and a half. I'm sorry. What's that? Yeah, then the other one.
Which
So-
one's usually better?
It's a toss-up between like trapezoid and midpoint. So for the trapezoid, I got 9 and a half. Let me just ask you, does it make sense? Even if it's boring and stupid, do you understand?
Yeah, but it's boring and stupid.
It is boring and stupid, I get it. Yes.
If someone came up with the area under the curve,
Yeah.
wow.
What's the point of this?
This what came first.
We have it. We know history class now.
Is the only rock
Yeah.
music you listen to the Beatles and Led Zeppelin?
I'm telling you, I didn't make it up, and I didn't put it on the test myself. Okay. Zach already spoiled it, but if you do find the actual area of this thing, it is 9.
How do we do that?
So,
The over.
that we start tomorrow, but you can find it on your calculator actually, or you can find it with antiderivatives, which is what we'll do tomorrow. But the actual area is 9.
Are we done now?
Now, we're not done.
She wants you to find the hexagonal sum. Just start using circles.
I said I hate everybody.
Where's the boy?
Okay.
Still gonna pair.
Okay. This is a really, I'm going to try to do it as fast as I can. They're going to give you a chart. And the chart's actually going to like make some sense, but I'm just going to give like whatever stupid numbers. And you're going to be asked to find, oh, sorry, let's go like find a left hand Riemann sum. The examples that we just did, the y equals x squared ones, each rectangle had the same width, so it was width. So they are called even intervals, okay, because each one had the same width. They don't have to have the same width to work. So very often you're going to be given a chart of data, and part of the question is going to say, find a left-hand Riemann sum. And it can say with uneven intervals as shown in the chart. So like my chart does not have even intervals, but it doesn't matter. The way I approach a problem like this is I'm really visual, so I make a little graph of my values. So like when x is 1, y is 4, when x is 3, whatever. I'm just going to make it sloppy, but y is 12, when x is 6, y is 8, and when this is 10, y is 2. So basically what this is telling me is I have some kind of curve that like goes through these points. I don't really know how, but it hits them somehow. And the problem is going to want you to find the area under that curve using a left-hand Riemann sum or a midpoint sum or whatever. So for this particular problem, you just need to know how to do it. I'm going to break all these into rectangles. And if I'm using a left-hand sum, then that means for this rectangle, I'm going to the left, and this is the height I'm using. For this one, I'm going to the left, and this is the height. And for this one, going to the left, and this is the height. So if I call this rectangle 1, 2, and 3, rectangle 1 is going to be base times height. The base is 2, and the height is 4. Am I going too fast? Shut up. Rectangle 2, my base is 3, and the height is 12. And rectangle 3, the base is 4, and the height is 8. put it all together, add it up, get your answer. We don't have to do that, but do you see what I'm saying? So sometimes it's going to be like it won't be a function given to you, it'll be a table.
Now we're done.
And you have to find it.
So then how do you know if that's like over and under?
You wouldn't. You wouldn't. Unless they actually showed you what traffic like. Okay, so seriously, punch Corey in the face. The homework is I actually found 3 open-ended problems that you can't do any of it other than the one part that's like squared up. We're not there yet, so whatever. I'm trying to find stuff that's applicable. So like you have a chart and they're asking you to
Just goes
find.
show you how useless this is.
Shut up. A midpoint formula. The next one is similar. And then if you have the book, you have the study book. I picked up 2 problems from there that are really good. But I know some people don't. So for the people who don't, I photocopied them and they're right here. So I wish I could take certain people's heads.
Certain people.
What?
I wonder what she means by certain people.
Wait, don't put these away. Let me just say one thing about it.
What? Just wait till I send you both. You won't want to smash my head like we're not. I'll help you cook that dinner.
For real, I did take a little time to like find all the stuff, so just listen for a second. In the first one, obviously, you see where I squared it up. Use a midpoint Riemann sum with 3 subintervals of equal length to approximate the integral of the function. Yeah, right. On the next one, use 5 subintervals indicated by the data in the table, blah, blah. This is going to ask you, is it an over or an underestimate? The second one is, again, the third one's from a table. On the next page, I didn't circle which one to do. It's 17 is which one to try. This is in the book, so like if you have the binder, you might, if you're writing in it, I would just do it in here. It's number 17 on page, whatever it is, 18. And then also on page 10, number 25. So I only photocopy them because I know everybody doesn't have a book. Whatever.
So only those 2.
Yeah.
17 to 25.
What's kind of nice about keeping track through the book is that like you start seeing all these problems done. It's like, okay, like we're advancing, and you can kind of see how far along we are and how much left there is to do and stuff. Thank you.